morning. My name is Charlotte Ng, and for 12 years, I was an art conservation scientist at the Los Angeles County Museum of Art, LACMA, where I studied a vast array of works of art ranging from Mayan ceramics to contemporary jewelry. 3 years ago, I left the museum world to work as a forensic microscopist at the Lawrence Livermore National Laboratory, investigating completely different objects, nuclear materials. Although I have switched careers, I was given this great opportunity to present a favorite topic of mine, which provided a lovely stroll down memory lane for me as I share with you my experience researching 3D printed objects. To follow up on Nick's talk, in the next 25 minutes, I'll be giving a broad overview of the many printing materials that are available, focusing on the ones that are more common. There are many 3D printing materials, and it would be impossible to cover them all, so I will just cover a few. The diagram shown on the left presents the interconnection of the design, material, and technology used to ultimately create a 3D printed object, in this case, a piece of artwork. The printing material selection will depend on the design. For example, if the artwork design requires a high level of detail, as well as the 3D printing technology that will be employed. For example, if that technique requires the starting material to be in a powder form. In terms of material types, the printing material can be wide-ranging. The most variety can be found in the polymers or plastics category. These materials can be categorized as either thermoset or thermoplastic. Thermoset materials undergo a curing process to become their final form. This is irreversible, much like cookie dough. Once the dough is baked in the oven and becomes a cookie, it will no longer be the thick, malleable, elastic paste that it once was. On the flip side, thermoplastic materials are those that can be melted, but they would still retain their original properties once resolidified. These materials are like chocolate, where even when it melts into a puddle on a hot day, once it returns to a cooler environment, it retains its delicious properties. Continuing with the dessert metaphor, composites are like chocolate chip cookies. Composite materials have two or more constituents that are disparate, but when combined together are synergistic and have enhanced properties. In addition to polymers and composites, 3D printing materials can also include many inorganic types of materials like metals, ceramics, glass, concrete. For this talk today, I will actually focus more on the polymers and metals, which are more commonly found and that were identified in a few 3D printed objects that were in LACMA's collection. Here on the right is a table that shows what materials can be used for the various 3D technologies. For vat photopolymerization and material jetting methods, thermoset resins are used that are cured by UV or visible light. This is what Nick mentioned when he was talking about stereolithography process. Thermoplastic materials can be printed using extrusion when it is in filament form, or powder bed fusion when it is in powder form. Metal powder is used in a number of methods that can be either directly melted or indirectly, the latter of which requires subsequent debinding and sintering after the printing process, and I'll get into that a little bit more later. So let's dive a little bit into the more common materials: photopolymers, thermoplastic, composite, and metal. First, I'll discuss liquid photopolymers that are used in 3D printing. It requires an energy source like UV radiation to cure the resin so that a solid object can be the end product. There are many photopolymers available, all consisting of 3 ingredients. The first two are monomers or oligomers. The polymerization of these reactants is induced by radiation and promoted by the third ingredient, photoinitiators. Photoinitiators are usually the free radical type or cationic type, the latter of which continues reacting even after the energy source is removed, so a consideration to keep in mind. The photoinitiators become excited when it absorbs the incoming energy, be it UV or visible light, and become reactive species that will instigate cross-linking of the monomers and oligomers to transform them into polymer networks. By carefully selecting and combining these ingredients, a wide range of mechanical properties from elastomers to rigid materials can be produced. Common photoinitiators usually use UV light, while monomer and oligomers are either acrylate-based or epoxy-based. Benefits of using photopolymers in SLA and material jetting applications are its ability to obtain high detail and being able to create watertight objects. Thermoplastic material more commonly used are nylon, PLA, ABS, PET, and TPU, although there are countless others like polyethylene, polypropylene, ASA, polycarbonate, etc., etc. Each material has their pros and cons in terms of how expensive they are, their mechanical properties, their long-term stability. Nylon is the most common because it has better mechanical properties, such as being able to resist abrasion and relative flexibility. It is also relatively stable under museum conditions particularly. However, one of the drawbacks of nylon is that it's hygroscopic, which can affect the quality of the final product and requires that the starting material be stored in a dry condition and also used dry. On the other hand, because it is hygroscopic, nylon can be dyed easily, which is what I actually found in the letter F object that came with our 3D printing kit. This object was printed using the SLS technique, although nylon can also be in filament form and be extruded. Under the microscope, you can see the object was not made in filament form and used under the fused filament fabrication method, as the surface of the letter is made of many, many fine grains adhered to each other. Also, under the microscope, I observed that in abraded areas, which likely occurred during shipment, some off-white areas peeking through. Given these objects were not art per se, I went ahead and did some destructive analysis and confirmed that indeed the black color was imparted during a post-processing step, as you see from the cross-section of the object. Another material that is a thermoplastic 3D printing material is ABS, acrylonitrile butadiene styrene. This is commonly used in fused filament fabrication, or FFF. ABS filament is extruded through a nozzle that is at an appropriately hot temperature, much like a hot glue gun works. ABS is considered non-toxic, which is a good thing because that's what Legos are made of, relatively stable under museum conditions, and not prone to off-gassing. Similar in process and properties to ABS is PLA, which is short for polylactic acid. Its key characteristics is that it is cheap, easy to print, and considered a renewable bioplastic and can be composted in high temperatures. However, long-term stability of the material is not fully known under museum conditions, and degradation of the PLA could lead to unwanted products. The blue rocket is an example of a PLA object. For transparent materials, PET, polyethylene terephthalate, or its cousin, PETG, is commonly used. This is the same material our soda bottles are made out of, and like ABS, reasonably stable under museum conditions. The last polymer I will mention is TPU. a thermoplastic polyurethane that also can be transparent and flexible. It's usually the smartphone covers that is made of. The green T in the 3D printing kit is actually made of TPU. TPU is composed of block copolymers that have both hard and soft segments. Given that the T that was provided is quite rigid, I suspect that there is a high ratio of hard segments to soft for this particular sample. Nowadays, more and more materials are composites, which, as I mentioned before, are made up of two or more constituents. Most common are thermoplastic material mixed with reinforcement fibrous materials like carbon fiber, so that the end product can be lighter and more dimensionally stable. Glass beads or bits of wood or metal can also be mixed in. Examples are shown on the right, where you see alumide, a nylon-based material used in SLS that has aluminum flakes to impart a metallic-like surface. In your 3D printing kit, you'll also find a wood-filled filament, which is a combination of wood powder similar to fine sawdust and PLA. The addition of wood is to impart a wood-like appearance and even smell, although I didn't smell anything from the sample in our kit. And you'll see that the bits of wood fibers interspersed within the predominantly PLA matrix in the image. The wood is usually a few tenths of a percent, and depending on the manufacturer, the wood particles can be from specific tree species, can be a mix, or even be not wood, such as bamboo or coconut. In the next slide, I'm going to interrupt our regularly scheduled program to talk about a case study of a composite that we encountered at LACMA a few years ago. I'll be doing this again once more when we also get into this metal section. A necklace came into the collection made by Ted Knowlton, which was to be put on display for LACMA's Beyond Bling exhibition. Fashionista Golden Girl, at first glance, didn't appear to be 3D printed by the naked eye. Only when we examined more closely with a digital microscope did we see evidence of the telltale steps or staircasing that indicated this object was indeed 3D printed. The steps appear to have been partially obliterated during a post-processing step. At higher magnification, we were able to distinguish clear spherical beads commingled with plastic grains that appeared to be partially attached to neighboring grains. Using Fourier transform infrared spectroscopy, we were able to determine that the clear beads were made of glass and that the plastic grains were made of nylon. Glass bead-filled nylon is indeed used in 3D printing to improve structural properties and reduce dimensional changes during the printing process. Also, do note the color gradient in the high magnification image. This is evidence that the necklace was probably dyed afterwards, as opposed to being printed with purple nylon powder. Of course, unlike the SLS nylon T sample in our kit, or F sample in our kit, I wasn't able to break off a heel of one of the shoes to find out for sure. The colorant and its light sensitivity was never identified, though if the object will be exhibited again in the future, microfade testing may be something to consider. Similar to the paint industry, where additives like dyes, fillers, plasticizers are introduced to the base material to improve its properties, 3D printing materials now have many ingredients. To combat degradation, be it during storage of the raw material or its end product, antioxidants, fire retardants, UV absorbers have found their way into 3D printed materials. Interestingly, the shift in view of the object being ephemeral prototypes to a stable product may be beneficial for those of us in the museum field. Although it is noted that like many traditional plastic art objects found in museums, 3D printed ones may pose significant conservation challenges in the future as the polymers inevitably deteriorates. In the future, one would expect new formulations and new types of polymers as manufacturers try to optimize their products to improve their working and mechanical properties from the materials. In particular, materials specifically designed for 4D printing seem to be on the horizon. 4D printing materials shapeshift in reaction to external stimuli like humidity or temperature. For this type of printing, it requires a combination of material type, which tend to be a blend of, say, PLA and TPU, for example, as well as a well-designed origami-esque structure design. As Nick mentioned, these types of objects may end up in museum or private collections, and it would be prudent for us to have a good understanding of how they were made and what they're made out of in order to identify approaches to their care as well as reprinting. Another significant category of 3D printing material is metal. The challenge in 3D printing metal is the high melting point. Although with high enough power lasers, metals can be melted directly. Two methods, DMLS and LMD, can achieve this. However, to get around needing to melt the metal directly, other 3D printing methods can be used. One method is to basically do lost wax casting, where a thermoplastic object is printed and then used to create a plastomold where molten metal can be introduced. Or the actual mold itself is printed in either sand or plaster. Recently available are metal-containing filaments, which are basically a thermoplastic material mixed with metal powder that is then extruded using fused filament fabrication. Once the object is made, it is then sent into an oven to debind, which is to burn off all the thermoplastic that is not desired in the final metal object, and then sintered to coalesce all the metal grains together to compact and densify the object. Another method is SLS, which has metal powder where metal particles are individually coated with a polymer. When exposed to the laser, the polymer melts and adheres neighboring metal grains together to make the 3D object. In this method, subsequent debinding and infiltration of another material is needed to complete the object. This leads me to two case studies that will highlight this interesting technology and its final products. The first case study is another contemporary piece of jewelry from the Beyond Bling exhibition at LACMA, the Doug Bucci's eyelet bracelet. Like Ted Knowlton's fashionista Golden Girl necklace, at first glance, this object did not appear to be 3D printed, aside from the intricate design that one would think would be difficult to create using traditional jewelry making methods. The answer revealed themselves under the microscope once again. For this bracelet, the outer surfaces were polished smooth, with some defects here and there. However, when you look through the bracelet to the inside surfaces, the characteristic step pattern was observed. Of course, these areas are difficult to access, and thus the staircasing couldn't so easily be polished away. Under high magnification, we saw islets of our own, golden islands in a gray-colored ocean. Interestingly, the two materials appeared fused together. With our handheld X-ray fluorescence spectrometer, we found iron, chromium, copper, and tin. The elemental analysis indicated that the surface was then made of regions of stainless steel, which explains the iron and chromium, that are then adjacent to regions of bronze, which is composed of copper and tin. This doesn't make quite much sense in traditional metallurgy, but it is found in 3D printed metal objects. We were able to put two and two together and confirm that this bracelet was made using indirect selective laser sintering. So how does it work? As mentioned previously, the starting material is metal coated with a thin layer of thermoplastic polymer. For this bracelet, the metal was stainless steel. Using SLS, the 3D object is printed using this coated metal powder. You can imagine that the object is very fragile, as the powder is only held together tenuously by bits of melted polymer. After SLS, the object is considered in a green state. The object is then gently removed from the SLS system and put into an oven where the polymer is burned off. However, if the polymer is burned off, nothing would be holding the steel particles together. Enter bronze, with its lower melting point than steel. Molten bronze infiltrates all the nooks and crannies of the steel via capillary action, filling up all the voids left behind by the binder to create a solid metal piece composed of the two different alloys. Once the object cools down, post-processing like polishing to a shiny finish is performed. As you can see, when it entered the museum's collection, the bracelet was in relatively good condition. Given what I knew from working on the next object I'm about to present, I will reveal an inherent vice that these types of 3D printed objects has. Similar to Doug Bucci's bracelet, Greg Lynn's flatware was made using indirect SLS. Instead of stainless steel, polymer-coated tool steel was used. Unlike the bracelet, the flatware exhibited condition issues, namely rust. It was noticed that some pieces of flatware was significantly warmer in tone than in others, which were a lot grayer as well. Handheld XRF analysis confirmed that the cooler tone flatware pieces had much less bronze and thus more porous and delicate. Enter inherent vice. The steel and bronze, in intimate contact with one another, can lead to galvanic corrosion, especially under high humidity or wet conditions. In this situation, the bronze acts as a cathode and the steel as an anode, which results in the steel corroding, sacrificing itself to protect the bronze. That is why rust was only found on the surface of these objects. It didn't help that some of the flatware pieces were incompletely infiltrated with bronze, so there were many pores, resulting in a lot more surface area where moisture can come into contact with the object. Seeing these results, the conservator went ahead and removed the rust and devised storage and display strategies for the objects, which included desiccants to remove the moisture from the environment. The last categories I only briefly mention are ceramic, glass, raw earth, and concrete. For ceramics, the 3D printed object is made prior to firing. Clay can be extruded, or particles of clay can be stuck together using thermoplastic binders that is then burned off during firing. Researchers have even found a way to create a stable silica resin mixture that can be used for SLA. Similarly, glass can be extruded in molten state, or silica particles can be mixed with a polymer that is then burned away during the sintering process to create transparent glass objects. As for raw earth and concrete, Nick's video of the house made of concrete reminded me of the recent habitats built in Italy made of soil, water, organic fibers, and binder, which are akin to rammed earth houses. In both cases, whether it's raw earth or concrete, the material has a dough-like consistency that is extruded like toothpaste to create the layers. I'd like to wrap up this presentation with one last topic, ways of looking at objects to determine whether they were 3D printed and perhaps with what method. A careful visual and microscopic examination is in order to find any obvious clues. Things to look for would be evidence of layering as shown in the center of the slide. Be warned that sometimes these steps could be obliterated during post-processing. For SLS, surface may appear to be composed of particle grains that are adhered together as shown on the right, which happens to be an optical micrograph of the letter I in our 3D printed kit. For fused filament fabrication, do take a look at your green T object in your 3D printed kit, and you'll notice the rounded layers created during the extrusion process. For extruded objects, you may also find flaws, such as those found in the blue PLA object that I had, where you see layers not fully adhere to each other, and deformations as it rounds the corners. In terms of analytical methods, I found it useful to use non-destructive spectroscopic methods like FTIR and Raman to clearly identify the base polymeric material for 3D printed plastic objects. This may require having a comprehensive database of FTIR and Raman spectra, or you may need to look in the literature to compare peak positions. For metal, it was very useful to have the handheld XRF instrument to identify the alloy elements in the material. In all identification methods, do be wary of being led astray. Post-processing can remove or introduce materials. For example, coatings may be present. Plastic objects can lend themselves to being plated with metal, and metal objects can sometimes be coated with polymer for protection. This may be found more commonly in printed jewelry in order to mitigate interaction between the metal jewelry piece and the skin oils, as well as moisture. I hope this presentation gave you just a taste of what 3D printed materials are available out there, how they're being used, and associated with the various 3D technologies available. 3D printed objects grew out of the prototyping field where longevity was never a goal. As the industry matures and focus is placed on additive manufacturing of products that are not prototypes, products hopefully will be more stable and have less preservation issues. It is thus very important for us to understand both the printing technique as well as the printing material to fully understand the challenges that we may face with objects of this nature. I'd like to acknowledge my former colleagues at LACMA, as well as the co-organizers of this conference, for allowing me to give this presentation. If there are any questions, please do not hesitate to reach out.